When you power on your microcontroller or hit the reset button, your microcontroller always goes through the same routine. It's a little bit different than what you might expect on a full desktop computer. There's fewer moving parts, which is kind of nice. Let's redraw our memory. And I'll just draw a simplified version of it. In specific, I'm just going to say there's this special bit here at the bottom. And that's where your bootloader lives. And what I'm talking about on this slide is specific to our ESP32S3. Most microcontrollers will more or less follow the same suit, but I am going to be a little bit specific to our microcontroller. Whenever you power on the device, it's going to jump to a very specific section of memory called the bootloader, and that cannot be erased on the ESP32. It's essential to the functionality of our microcontroller. Other microcontrollers, you can actually override this part if you wanted to. Maybe you have better functionality that you want to run immediately upon restarting the chip, and you don't want to waste that extra memory, even if it's only just usually a few hundred bytes at most. For the ESP32, essentially what this does is it runs a little bit of setup code and then immediately jumps to a second stage bootloader. And that is something we can have control over. This second stage bootloader, for example, could be the Arduino bootloader. Or maybe the Toit bootloader. And they, in their documentation, usually refer to it as the Toit virtual machine. We'll talk about it more when we get to the Arduino bootloader portion of our lecture. So I'm just going to skip this for now and say that the second stage bootloader can really be whatever you want it to be. I should also mention a couple of the things that the original bootloader will do. The first code that's ever executed. It's not extremely important to realize this, but it can do things like check for over-the-air updates. More importantly, though, it can do security checks. You can set up the microcontroller so that it's sort of less tamperable. You're more likely to detect if somebody's made some change to it. Alright, the last thing that I'll mention here is that the second stage bootloader is then in charge of jumping to whatever your application is. So for example, if we wanted to blink LEDs or drive some motors, that's code that we more directly have access to. In this class, we'll be using the Arduino bootloader. We're never going to edit that code at all. Instead, we'll let the built-in bootloader call the Arduino bootloader, which is then responsible for jumping into our code after it's done its setup. Since we spent so much time talking about Toit and Jaguar, I think it's worth mentioning a little how it differs from what we'll be using going forward. So you have your microcontroller and the bare metal that it's running on. It sets up a bootloader, or it inherently just has an internal bootloader that can't be changed, which then is going to call the Toit virtual machine. The Toit virtual machine is essentially a behemoth. It is the program running on your machine, on your microcontroller. That's why they don't really call it a bootloader, is because it doesn't stop. It's not just loading your program. It is the thing that is going to run for the entirety of the operation of the microcontroller until you shut it off or flash something over it. So what does the Toit virtual machine do? You can think of it as just having a loop where it'll do something like it'll execute a user instruction, and it'll just continue to do that in a loop, while behind the scenes, after executing each of your instructions, it'll do something like garbage collection, or sending something over Wi-Fi. In fact, the general term would be just to manage this, would be to say that it manages the system. Any instructions that you write in TOIT are going to be checked by the virtual machine. So if you have something wrong in your code that's syntactically correct, meaning it'll compile just fine, but semantically doesn't make any sense, maybe you're using a pin that's not a valid pin number, the TOIT virtual machine will check for things like that, which is why we started with it this semester. You're less likely to have a catastrophic error when using the TOIT virtual machine. So the last thing I'll put on this picture is your application. I think I will abbreviate that app. Something that we didn't get into and that wouldn't be useful for us is technically you're allowed to have multiple apps running on the TOIT virtual machine at any given time. So you could have one that's running the robot and another that's, I don't know, watering the plants, completely separate functionality. They can interface with different hardware. They can actually, in fact, use the same pins as long as they share them nicely. So what does the picture look like for the more traditional experience that we'll have for the rest of the semester? We have the microcontroller. It'll run its bootloader, which will call into the Arduino bootloader, which immediately just jumps into your application. And at no point in time do we jump back down. That just does not happen. Instead, your application is given full control over the system, for better or worse. Before moving on, though, I think it's also good to motivate just how strong of a value proposition the TOIT virtual machine actually gives us. Here is the familiar blink code. It's a nice syntax, probably familiar to anybody who's programmed in Python. We can import a GPIO library, set a pin to be an output, and then set it high, set it low, and in between delay 500 milliseconds each time. So what's actually happening here is once this compiles to bytecode, so this gets turned into TOIT bytecode, which looks pretty similar to assembly code, the TOIT virtual machine will execute the instructions in a loop. It'll say, okay, execute the instructions needed to set a pin to 0. Then, when it sleeps, it'll set a timer, and you don't have to worry about sort of what happens behind the scenes. The TOIT virtual machine, though, is likely to use this time cleverly. When you say sleep for half a second, it's not just going to shut everything down. Instead, it's going to use that time to do something like send a message across Wi-Fi or maybe perform a garbage collection task. You, as the writer of TOIT, are basically just saying, I don't need you to do anything in specific for the next 500 seconds, or 500 milliseconds. This gives us a lot more power than you might be expecting. Here's a slightly more advanced version of this same program. Both of these are identical to what we saw before. They're just blinking LEDs. Both at both at different rates, actually. One on and off every second, one on and off every quarter of a second. These two tasks are being run concurrently. Try to imagine writing the code in a single loop up here. I should also mention this task syntax is how we have TOIT launch these tasks as separate threads of control flow. It probably sounds easier than it actually is to combine both of these into a single loop. They both start out with while true, and then they both sleep. But in the case of the task 2, we only need to sleep 123 milliseconds before turning LED 2 on. And then we would have to say, okay, well, sleep an additional whatever 500 minus 123 is. Oh, actually, I can't do that because LED 2 needs to be turned back off before I do anything with LED 1. The point is, this task of writing this in a single loop is going to get a little bit obnoxious pretty quickly. We will have to do it that way when we abandon TOIT, but it's worth seeing the value that TOIT adds before we just get rid of it. What TOIT actually does is it'll just run these as separate threads of execution. So we would have task 1 and task 2. It doesn't matter which gets scheduled first, but they have what's called a cooperative style mode of execution. So one of them will run, and then it'll hit its sleep, and it'll yield time. And that means that TOIT feels perfectly fine to run thread 2, which will run, picking up wherever the first one slept, and it calls sleep. And TOIT then knows which one is going to wake first, which in this case would be task 2. All task 2 needs to do is wake up long enough to set LED 2 to 1, and then it sleeps again. And it knows that it's the next one to wake up again to set LED 2 to off before it sleeps again. And every time it sleeps, the TOIT virtual machine is checking to see if it's time to run code for thread 1 or task 1. And that's stuff that's processing that you don't have to think about at all. You just let the TOIT virtual machine handle it for you. So the question then is, why leave TOIT? Well, when I started adding additional peripherals, I started getting a lot of out-of-memory errors, even when only 8% of the unit was actually being used. There are just a few bugs and kinks that are not quite worked out of the system yet, and I didn't really realize that until I'd been using it long enough. One more reason to use TOIT is to show you one of the alternatives. So at one end of the extreme is something like TOIT, and using the ESP IoT development framework, the sort of baseline bare metal way of dealing with our microcontroller, the ESP32S3, is to use ESP IDF, which looks like these two boxes here, to do that same blinking code. You can see largely the code is pretty similar. We have some setup code for configuring the LED. This is taken directly from their documentation. And what that does is it sets the LED to an output pin, and then it calls blink LED in a loop, and calls vtask delay instead of sleep in the loop. So not too bad, but doing this same code with two LEDs blinking at different rates would be a bit of a nightmare to write. So we're going to have a bit of a happy medium using the Arduino ecosystem, which I'll introduce in the next video.